Hello, honors physics students. All right, let's go ahead and start here with problem 29. I want you to do parts A, B, C, and D on your own. Pause the video as you do so. Come back to see how I go through it. Okay, so we just finished our whole analogy with the hiking trip where the mountain represents this difference in potential. Potential is a way to visualize like elevation. And the moving object is either the cooler of food if it's a positive charge, or the helium balloon if it's a negative charge. Here we're dealing with a positive charge, so it's going to be our cooler of food as we're imagining what's happening here. And the potential is our analogy for elevation. And so a high potential is like a high elevation, a low potential is like a low elevation, and we know that when we're talking about the cooler of food, it takes a lot of effort to bring it up to the top of the mountain. That's like a positive charge going where it doesn't want to go. It's got a lot of potential energy once it's there, which means that positive charges create high potential. If you were to let it go, it would naturally roll down the mountain to a lower potential. That must be where the negative charges are. And so in any system, the lowest potential will always be the negative, and the highest potential will be the positive in this case. And so the low potential is the 0 volts. That's going to be the negative plate. The 210 volts is going to be the positive. So for letter A, we're just going to label the left-hand plate here with positive, the right-hand plate here with negative. Nice and simple there. The low potential doesn't always have to be 0 volts, although lots of times we do just set it equal to 0, just like we can set a height equal to 0 in terms of gravitation. Think of it sort of like sea level. All right, so letter B, how much work would it take to get this charge? First of all, is this charge a proton? Automatically, you should definitely say, of course, it's not. Look at this charge. There's no way there's a proton. All right, so how much work is it going to take? So we could say W equals F delta X cosine theta, except we don't have delta X, and we can't do that, right? But we do have to change the potential. And so we should be thinking about the equation with potential difference and rearranging it to solve for work. Oh, sorry, I did forget it here. We should always be drawing the field lines, and hopefully you already did that. I did ask you to do that in a previous video, and that should just be a matter of course. Now we know positive on the left, negatives on the right. Just draw the field lines in this case so we can see which way the field is pointing. Okay, so here we know we're looking for the work done by the field, because that's what the problem is asked for, the work done by the field. That's going to be negative Q delta V. Always pay careful attention as to who's doing the work. Specifically, it does say the work done by the field, so make sure we are doing W sub E. If you're writing this equation without that subscript E, 1, that's incorrect, but 2, you're not going to think about it in the correct way, right? The work done by the field is the negative Q delta V, and of course the delta we always separate out into final minus initial. So which is final, which is initial? Well, all you have to do now is just read the problem carefully. It does say it's moved from the negative to the positive, right? So the negative is the starting, the positive is the ending. So in this case, what's going to be 0? That's going to be V naught. It's moved from the negative, so it starts here at 0 volts. That's going to be the initial potential. It's going to end here at 210, so it's got to be 210 minus 0. When you put your numbers in, the negative sign is part of the equation, so we should not lose that negative sign. That has to be there. In the end, we should be getting negative 1.05 times 10 to the negative third joules. Okay, now let's make sure this is making sense. We're saying the field itself is doing negative work. Why would that be? Well, to understand it, we can go back to our equation, W equals F delta X cosine theta. The sign on the work really depends on the angle theta. So now we want to remind ourselves, where's theta measured? We already reviewed this recently. Remember, theta is always referring back to the two previous vectors, between the force and the motion. So we look back at our picture, here's our positive charge, and here's the field it's sitting in. Which way is the force that the field is applying to it pointing? How do we know? Well, as always, it's about rule number 1. I'm not going to keep writing rule number 1, but you should always be thinking about it, right? Field lines show the direction of the force on a positive charge. And so the positive charge feels the force to the right, which makes sense because that's where all the negative charges are. Which way are we moving it? We're moving it from negative to positive, so we're moving it to the left. The force is to the right. What angle is that? That's an angle of 180 degrees. Cosine 180 is negative 1. So we should be expecting the work done by the field to be negative. We got the work done by the field to be negative. Everything is making sense. Fantastic. Okay, let's visualize this, though, in terms of gravitation. So let's say we have, instead of oppositely charged parallel plates, we have a gravitational field, and we're going to move an object in the same general direction. Which way would you be moving an object so it mimics what's happening here? Let's think this through. There's a positive charge. We're moving it from negative to positive. So does that mean we're giving it extra potential energy or taking potential energy away? Is it going where it wants to go or not where it wants to go? It's going towards the positive plate. That doesn't want to be by the positive plate, so we're giving it extra potential energy. So if you have an object here, you're moving it up, right? From a location of low potential energy to a location of a lot of potential energy, moving it away from where it wants to go. So this is what we want to visualize, taking a mass and moving it up. Okay? So now the question asks about the work done by the field. So we draw a little free body diagram. Oh, sorry, we say it's moving up and then draw a free body diagram. And of course, there's weight pointing down and the force you're applying up. And here's our equation, W equals F delta X cosine theta. Now we're focusing on the force of the field. If you're focusing on your force, well, here's your force, right? You're moving it up, and you have a force pointing up, so that's an angle 0 degrees. You're doing positive work. But the force of gravity is pointing down. That's the force from the field. The object is moving up, but the field force points down. That's an angle of 180 degrees, and so while you are doing positive work, the field is doing negative work. And as long as the object is moving at a constant velocity, and unless the problem says otherwise, we can assume it is, we can pretty much always say this, that the work that you do will be the opposite in sign of the work done by the field. And if you go back to when we've done gravitational potential energy the first time, you see we've done a very similar idea. So that's what's going to happen here as well. And even electrostatic effects, the work that you do will be pretty much almost always opposite in sign to the work done by the field. Which brings us to letter C. If you were the one moving the charge, how much work did you do? Well, now we apply that idea. The work that you do is the opposite of the work done by the field. So literally just take this amount and take the opposite sign. Alternatively, you could have said the work is the change of potential energy, but that's really what's answered here in letter D, that when you do work pushing this positive charge towards the positive plate, you're storing electric potential energy in the system. That change of potential energy is the work that you did. And if you go back to gravitational effects, it's the exact same idea. As you lift an object up, your work becomes the gravitational potential energy, or the change in gravitational potential energy of that system. So you don't even have to show extra work for that. It's all the same number, just a matter of who's doing the work. This is the work done by the field, this is the work done by you, and of course, as a result, you give the system potential energy. Not to be confused with the equation that said that the negative of the work done by the field is the change in potential energy. It's all about the negative signs, being very, very careful with them. Alright, let's go on to letter E. How far apart are the plates? So go ahead and, for letter E and F, pause the video, answer those on your own. Okay, so now that we have the change of potential energy, we're just going to use that equation, solve for delta D, nothing fancy here. You're going to get 0.03 meters. Again, it's not a proton. We know what the charge is. The charge is given. Just go ahead and put it in. Nothing fancy. Okay? And that's a typical sort of number. That's 3 centimeters. And very often in these systems, and these, by the way, are describing real systems used in actual laboratories, often the plates creating the field are pretty close to each other. So 3 centimeters, that's a typical sort of number, even for a very large field of 7,000 newtons per coulomb. Letter F, what will the charge do if you let it go? Well, we have this positive charge up against the positive plate. What's going to happen? Of course, we know it's going to move to the right, but that's not really enough. What's going to happen as it moves? Well, there's a force applied, right? Which means it's going to accelerate. It's not just going to move, it's going to accelerate towards the negative plate. It's going to pick up speed. We can do conservation of energy or forces in kinematics, and we've done that in previous problems. Okay, let's look at this though. You should notice when we did this delta D equals delta P over QE, that here we have change of potential energy over Q. And if you look at the equations, that's the exact same thing as change in potential, which means we could just have replaced that with delta V over E and found the change of position that way. In fact, if you want to just quickly do the calculation, the change of potential, of course, is the 210 volts divided by the field strength. You're going to get the change in position there. This forms a nice little shortcut. So going back into our notes, let's rearrange this for delta V. So we're going to write it here as delta V equals E delta D. This makes a really nice shortcut for finding the potential difference between the plates. And notice it takes the charge out of it. It's not going to matter what charge it is. Now, it gets a little bit confusing as to whether this will be a positive or negative, so we're just going to alter this by putting some absolute value signs around both sides, and now we can go ahead and box it in, and this will be our shortcut equation for finding the potential difference between plates, relating it to only the field strength and the distance of separation of the plates, and having nothing to do with the charge itself. But we do have to keep in mind this only for uniform electric fields. This only works for plates. There are other systems we can look at, and we will look at some of those, but this will only work for fields, for uniform fields. Whereas these equations for potential difference are all-purpose equations. These will work no matter what. But one of the strong points of this equation is that it does take the charge out of it. Because remember, back in our hiking analogy, we said if we never actually take the hike, if we never move that cooler to the top of the mountain, does the mountain disappear? No, of course not, right? So if we take the charge out of the picture, these plates are there. They create this potential difference whether or not there's a charge moving around between them, whether or not there's a charge to experience that change in potential. The plates themselves basically are the mountain. This is the top of the mountain, this is the bottom of the mountain, and they create that potential difference just like the mountain is there, creating a change in height ready to be scaled or not. It doesn't matter. The mountain's always there, the plates are there creating the field, and this is a great equation that really brings that into focus. Now let's just take it from one more different perspective. Let's put that positive charge back in there. Okay, so let's say I take the positive charge, which is like the cooler food, and I let it go. Where's the cooler food go? Of course, it rolls down the mountain, and the positive charge accelerates towards the negative plate. Great. Okay, now the question is, in doing so, is it gaining or losing potential? well, it's going from a higher potential to a lower potential, so of course it's losing potential. We know that. But what about potential energy? Is it gaining or losing potential energy? Just pause the video and think that through. Well, I just shown you the example of this in terms of the mass, right? If the mass were going to a lower height, it's losing potential energy. So this positive charge is also losing potential energy, right? It's going to a place where it wants to be. And it could be shown here with the equation as well. Here's the equation relating the change of potential to the change of potential energy. All right, so let's think about this, right? So if the positive charge moves this way, is moving up or down the mountain? That's down the mountain, right? It's losing potential. So is delta V positive or negative? I hope you said that's negative, right? If it's losing potential, that's a negative change. Okay, so this term here is negative. The charge itself is positive. Remember, no absolute value here. So if this is negative and this is positive, this term must be negative, which is what we just said. Right? It's going where it wants to go. It's losing potential energy. Everything's making perfect sense. However, what if it's a negative charge? If I let the negative charge go, where does it want to go? Well, it's like the helium balloon, right? It likes to rise, which means it's gaining potential. Okay, so as this negative charge goes up towards the positive plate, is it gaining or losing potential energy? What did you say? Oh, wait a second. It's going where it wants to go, right? That's losing potential energy. Any object that's going where it wants to go loses potential energy. And if that still confuses you, let's look at the equation. All right, so it's a negative charge. It's gaining potential. So delta V, is that positive or negative? That's positive, right? The charge started here and it's moving up the mountain to a higher potential. That's a positive delta V. So this term is positive. The Q itself is negative. And so if this is positive, this is negative, delta PE must be negative to make it work. And so we see anytime the charge is let go to go where it wants to go, it's always losing potential energy. That's just what potential energy means, right? When an object has potential energy, it's a place where it doesn't want to go. When you let it go on its own, it goes to a lower potential energy. And so I find that most students really get one or the other. They really get this change of potential or the change of potential energy. So if I were you, I'd focus on one or the other, and then the connecting equation is right here. As long as you're good with your signs, you can always get to the other way of thinking about it, whichever works better for you.